In this section, section 3.2, we talk about continuity, and we use limits to introduce continuity mathematically. So let's start with continuity. What do we mean by continuous function? A function is continuous if we graph that function, and we can graph that function without need to pick up the pencil. And we can start at any point here, let's say at this point here, and graph without need to pick up the pencil. We can reach any point, other point here, without the need to pick up the pencil. So that's what we mean by a continuity intuitively. But what we mean by continuity mathematically, let's start with some graphs. The first graph, this is graph number 1, and the function, let me graph it in blue. This is f of x. And graph number 2, graph number 3, and graph number 4. Okay, now look at these graphs of function. The first graph of function f of x, this function is continuous. As you can see, you can start at any point and end and reach any point in that graph without need to pick up the pencil. Now we want to pay attention to some important points. The first thing, suppose that this point here is 3 and this point here is 2. Now what is f of 3? The image of 3, f of 3. f of 3 is 2. That's the value of the function under the at the value x equals 3. So f of 3 equals 2. That's the image. Now what about the limit of the function? Limit of the function as x goes to 3. As x goes to 3, if we start here to the right of 3, we notice that the graph goes into the direction of, as we approach 3 from the right, what happens to the values of the function? They approach 2 from the right, from here, from above. So when limit x goes to 3, let's write it as 3 from the right. I mean 3, we write it as 3 plus of f of x. This is 2. Now what about limit from the left? I mean from here. As x approaches 3 from the left, what happens to the graph? The graph approaches 2, and that means we can write it this way. The limit from the left is equal to the limit from the right, and that means this is the value of the limit. It's 2. And as we can see, at the point x equals 3, the image of the function is equal to the limit. And that's why mathematically this function is continuous at the point x equals 3. So in order for a function to be continuous at the point x equals 3, the image of the function, or the value of the function at 3, should be defined, should give some value, and the limit at that point should exist, and that means it gives us some real number, real value, and the limit is equal to the image. Those are conditions for continuity. Okay, so the first graph is continuous. Let's go to the second graph. For the second graph, as you can see, at x equals 1, the function is not defined because we have a hole here, and that means the value of the function is undefined. The value of the function at x equals 1 is undefined. But what about the limit? Limit of the function, as you can see, the limit, if you start from the right, the limit is the height, it goes to 1, and if you start from the left, you will approach 1. So the limit is 1 from the right and from the left. Limit does exist, but the value of the function is not defined, and then we have a problem. So those are not equal. That means the function is not continuous. So the function is discontinuous at one point, at x equals 1, but it's continuous here at x, for example, equals 2. It has an image, and the image is equal to the limit. So here this function is discontinuous, and this discontinuity is called removable discontinuity. Removable because we can define a point here that can close this circle. Okay, so removable, that means we have a hole. Okay, now what about the number 3? Number 3, as you can see, it's discontinuous because just look at the graph. It consists of 2 separate or disconnected parts, so it's not continuous. Mathematically, what is the value of the function f of t? F of 2. F of 2 is 1. So it's defined. We don't have any problem here with the value of the function. What about the limit of x goes to 2? Here we need to study the limit from the right and from the left. When x goes to 2 from the right, I mean here, what happens to the value of the function? It approaches 2. What about limit from the left? X goes to 2 from the left. From the left, the value of the function approaches 1, the height 1, and those are not equal, so limit does not exist. And that's why the function is not continuous at 2. The image is not equal to the limit. Limit does not exist. So we write here this type of discontinuity, let's call it jump discontinuity. Imagine that in order to continue on that curve, you need to jump here, right? So let's call it jump discontinuity. Now the last type of discontinuity appears from figure 4. We have what is the value of the function at 4. It's discontinuous, but because by just looking at the graph it's disconnected, so it's discontinuous. Now what is the value of the function at 4? We don't have an image, so look at here, look at the function here, we don't have an image, so this is undefined, and that means it's discontinuous. If one of these conditions is not satisfied, that means the function is discontinuous. Now let's find the limit. Limit as x goes to 4 of f of x. Now here we need to study limit from the right and from the left. What is limit as x goes to 4 from the right? From the right, the value of the function goes to negative infinity. And from the left, when x approaches 4 from the left, what happens to the value of the function? It goes to infinity. So that means limit does not exist. And this type of discontinuity is called infinite discontinuity because we have infinity here. Infinite discontinuity. So we can summarize the conditions that if they are satisfied, then the function is continuous. So we say that the function f of x is continuous at x equals a is some value, if the following conditions are satisfied. First, f of a, when we plug a into the function, we get a value, a real number, if this is defined. And the second condition is that the limit of the function f of x as x approaches a does exist. And the third condition is that the image f of a, this is called image, is equal to the limit. So those are the three conditions. Now here we dealt with continuity by focusing on a graph of the function. Now let's take some rules of function and study those functions algebraically. So if we are given the function f of x equals its piecewise defined function, I mean a function that's defined by more than one rule, less than or equal to 1, and 5 minus x that for x is greater than 1. Now here we ask, is the function f continuous at x equals 1? As you can see, 1 here, the function is defined by more than one rule around 1. So when the values of x are less than or equal to 1, then we need to plug into this value of this part of the function. When x is greater than 1, we plug here into 5 minus x. So that's why the function is called piecewise continuous. When we graph it, we get a graph that consists of two pieces, or we have two rules of the function. Good. Now we want to study continuity, so we first find the image, the value of the function. The first condition is f of 1. F of 1, where should we substitute 1? As you can see, we have equality at 1 here, so we plug here into the first rule. So we have 1 plus 3, which is equal to 4. It's defined. Good. Now what about the limit? Now we need to find the limit as x goes to 1 of f of x. But here the function is defined by more than one rule around 1. So we need to find the limit from the right and find the limit from the left. The limit from the right, that means x is greater than 1 here. So the rule is 5 minus x. And then we plug 1 here. We get 5 minus 1, which is equal to 4. Good. What about limit of the function as x approaches 1 from the left? From the left, that means x is less than 1. So we plug into the first rule. So this is limit x goes to 1 from the left, x plus 3, and then we plug 1 here. We get 1 plus 3, which is equal to 4. As you can see, limit from the right is equal to the limit from the left. And that means the value of the limit when x goes to 1 is equal to 4. Now notice that f of 1 is equal to the limit of the function as x approaches 1. This is equal to 4, this is equal to 4, so the function f is continuous at x equals 1. Let's take another example. if we define g of x as a piecewise continuous as a piecewise defined function x plus 3 when x is less than or equal to 1 and 1 minus x if x is greater than 1. We want to check if the function f continuous at x equals 1. We apply the three conditions. The first condition, f of 1. What is f of 1? We have equality here, so we plug into this rule. So 1 plus 3 is 4. So it's defined. Good. The second condition, the limit as x approaches 1 of f of x. Now here the function is defined by more than one rule around 1. So we need to study a limit from the right and from the left. From the right, x is greater than 1 because it goes to 1 from the right. We apply 1 minus x. And then we plug this value here. So we get 1 minus 1, which is equal to 0. What about limit x goes to 1 from the left? Here, x is less than 1. That means we plug into this rule, x plus 3. And then plugging x equals 1 here, we get 1 plus 3, which is equal to 4. As you can see, limit from the right is not equal to the limit from the left. That means limit of the function f of x, x goes to 1, does not exist. And so it's not equal to the image. So we can say that f of 1 is not equal to limit of the function as x goes to 1. And that means f is discontinuous at x equals 1. Let's do another problem. If we define h of x, sorry, here I used g of x, and then when I did everything else I wrote f of x. So let's change the function into f of x. It doesn't matter, f of x, g of x, those just are symbols or symbols that we use to represent function, or letters. We usually use small letters for functions. So we can write f of x, g of x, h of x to represent functions. Now let's do the following example. We have h of x defined by 1 over x if x is not equal to 0, and 0 if x equals 0. Now for this function, we ask, is the function f continuous at x equals 0? So let's apply the three conditions. The first condition, f of 0 is, where should we plug 0? Here we have equality, so this is constant function, so f of 0 is 0, so it's defined. Second, limit as x goes to 0 of the function f of x. Here we don't have limit from the right, from the left, because here, as you can see, when x is not equal to 0, that means from the right and from the left is 1 over x. So we have x goes to 0 from 1 over x. Now we can study limits from the right, from the left. So when limit x goes to 0 from the right, 1 over x, if you plug a value that's very close to 0 from the right, I mean, let's choose a value like 0.001. You get 1 over 0.001, which is 1 over 1000, and then flip the denominator, you get 1000. If you add more zeros here, you need to add more zeros here, so you get, what happens to the value of the function? Sorry, it gets bigger and bigger, so that means it goes to plus infinity. Now let's study the limit for as x goes to 0 from the left. From the left, let's choose a value that's very close to 0 but from the left. Let's choose negative 0.00001. Now here we can plug it into the function, we get 1 over negative 0.00001, and this is negative 1 over 1 and 5 zeros, that means 100,000, and then flip the denominator, you get 100,000, and that's very large negative number. If we add more zeros, we get more zeros here, and that means we are approaching negative infinity. Since limit from the left is not equal to the limit from the right, that means limit does not exist. And that means f of 0 is not equal to the limit of the function as x approaches 0, so limit does not exist. And the value of the function does exist, that means the function is discontinuous at x equals 0. If you want me to visualize this function by graphing it, if we want to graph this function, the function is 1 over x. 1 over x looks like this, 2 pieces, when x is not equal to 0. But what if x equals 0? If x equals 0, then the value is 0. So at 0, we have 0 here. So the function here is discontinuous, actually, by just looking at the graph. The value of the function, this is f of x, it consists of 2 pieces. So f of 0 is 0, and the limit, when we take values that are very close to 0 from the right, what happens to the limit? The limit goes to infinity. And if we take some values very close to 0 from the left, what happens to the value of the function? It goes to negative infinity. So that means limit does not exist. Now the last example in this video is if we have f of x, and here I had the same situation. I use h of x for the function and then used f of x. So let's call it f of x. Sorry about that. If I use h of x here, I should use h everywhere. Now f of x is x cubed minus 8 over x minus 2. Where's the function discontinuous? This function is discontinuous at the zeros of the denominator. So if we have fraction or rational function, then we look at the zeros of the denominator. What is the value of x that makes the denominator equal to 0? X equals 2.